Okay, question 3.5.4 asks you to find out the probability of y is greater or equal to 2. You only have to find out all the qualified categories like y equal to 2 and y equal to 3, which is greater than 2, and find out all the corresponding probabilities, which is 0.189 and 0.027, and add them up. And similarly, you can do the same thing for the probability of y smaller or equal to 2. 3.5.5, you want to find out the mean of this population. So what you want to do is to find out all the possible outcome and multiply it by the corresponding probability and then sum them up. So this is how to do this in R, which is pretty straightforward. Use 0, the first outcome, multiplied by the probability of seeing 0, and the probability of seeing 1, which is 0.441, multiplied by 1, so on and so forth, and you add everything up, and that is the sample mean, which is 0.9 in this case. However, I want to point out that there is a more elegant way to do this, in which you can name two separate vectors, the vector of outcomes and the vector of probabilities. Simply multiply these two vectors together, and what happens under the hood is these two vectors will be multiplied element-wise, which means the first 0 will be multiplied by the first probability. So if you run this line of code, as you can see here, you get 4 different results correspondingly. Of course, you want to sum them up in order to get the population mean. And here you go, it is 0.9, which is consistent with what we got before. Although this does not necessarily make this question much easier, but it actually shows you how to use vectors in R and how to do vector operations. 3.5.6, you are supposed to find out the standard deviation of this random variable. So as you might recall from the class, what we are going to do is to find out the difference for each of the possible outcomes, find the difference between that outcome, for instance 0, with mu, which is the population mean we just calculated in 3.5.5, and then square that difference multiplied by the corresponding probability, and then we sum up all the 4 cases. So here is how to do it in R. As you can see here, I already called the mean that we found as mu. So the mu here, if you run this line, is 0.9. And what I'm going to do here is, for each of the case, for instance, the first one, 0, subtracted by mu, which is population mean, and square this difference multiplied by the probability of the first outcome. And similarly for the second one, the second possible outcome is 1 and the mean is mu. It's still the mu, as you can see. They are all mu here. So square the difference and multiply it by the corresponding probability, which is 0.441. So you are supposed to do the same thing for all the 4 cases and then sum them up. So in this case, you got 0.63. However, this is how to calculate the variance, and in this question, you are supposed to produce the standard deviation. So you have to take the square root of the variance so that you end up with the standard deviation. So that's it for the first 3 questions, but there is one thing I really want to mention is if you really read closely about the background information of 3.5.3, you will realize that this is actually a binomial distribution. And this kind of knowledge can actually bring us a very different approach to solve the next 2 questions, 3.55 and 3.5.6. Because based on the background information, the n, which is number of trials in a binomial distribution, is 3, and the p, which is success rate in this case, is 30%, which is 0.3. So we can apply the formula in binomial distribution to calculate mean and standard deviation rather than using a generic version. So let's take a look. This is actually a binomial distribution in which n equal to 3 and p equal to 0.03. So if you don't believe me, you can calculate this yourself. This gives you the probability of y equal to 0, and this should be equal to 0.343, which is calculated by the textbook. So as you can see here, it's the same. And if you calculate the probability of y equal to 1, which is 0.441, and that's the same with the textbook. And you can do the rest of the 2. My point is, as long as you recognize this is a binomial distribution, you can calculate the mean by using the formula for binomial distribution specifically, which is MP. So as you can see here, is 0.9, and this is consistent with what we've just calculated. And what about the standard deviation? It's given by square root of p multiplied by n multiplied by 1 minus p. So this is 0.79, which is the same with what we just did. But because we have recognized this is a binomial distribution, we can use a binomial distribution shortcut rather than using the generic version to calculate the variance. Okay, all of these questions, they are about binomial distribution. First and foremost, in order to do calculation for a binomial distribution or binomial variable, you have to know what is the n, which is number of trials you have implemented, and p, which is the success rate. So let's see how to do this kind of problems. 3.6.1, the p here is 0.75 because the ratio is 3 to 1, so that means the probability of seeing a yellow one is 0.75. I defined yellow as a successful trial. You can define green as a successful trial as well, but the p will be changed to 0.25. It doesn't matter which way you go, but it matters that you are consistent. Also, the n, which is sample size here, is 4. So the first thing we want to calculate is y equal to 3. There are 3 yellows, so you have to rely on this R code, d binom. So that is 0.4218. And similarly, in order to get all of them being yellow, you just change this 3 into 4. Lastly, it is asked what is the probability of all 4 of the same color. Actually, that boils down to 2 different scenarios. One of them is all green and the other of them is all yellow. Combine these 2 scenarios. This gives the probability of all yellow. But what about all green? All green means no yellow, so change 4 to 0. So you combine these 2 cases and the probability is 0.3203. This one is almost the same. You only have to figure out the different p and n. As you can see here, the p is 0.16 because according to the background information, 16% of adult population is nearsighted in Australia. That's where it's coming from. And by the way, n is equal to 3. You have 3 trials because you have 3 Australians. So we run these 2 lines of code. Interestingly, if we define p as 0.16, it will erase what happened before. In this case is p equal to 0.75. In previous case, it will be erased. The first question asks 2 are nearsighted, which means we have 2 success trials. And the number of trials is n, and the success rate is p. So the probability of seeing 2 are nearsighted is 0.0645. Next up, you want to find exactly one of them being nearsighted. So replace the 2 by 1 and rerun this line is 0.338688. And next up, what if we want at most one of them is nearsighted? This is a little tricky because it incorporates more than one case, because one of them is, exactly one of them being nearsighted. Another case is nobody is nearsighted among the 3 people, which is also a qualified case. So we have to calculate both of these 2 scenarios, the probability of them, and then sum them up. And next, what about none of them being nearsighted? And that means we have 0 successes. That is given by this. 3.6.6 is as straightforward as it can be because there are formulas that we can plug in order to get the mean and standard deviation of binomial distribution. The mean is np and the standard deviation is square root np1 minus p. So we can just plug the mean as a no-brainer. The mean is 10 multiplied by 0.6. Because according to background information, 60% of the individuals have streaked shells. That's where 0.6 is coming from. And the standard deviation is given by square root 10.6 and 1 minus 0.6. You multiply these 3 quantities together and take the square root. So if you run these 2 lines of code, the mean is 6 and the standard deviation is 1.549. 3.6.10 is actually almost the same with the first 2 questions. I mean 6.1 and 6.2. It might be confusing to see that number, that 300,000, but I think that one is irrelevant. It's just distraction. you only need here in this case n is 8 and p is 0.7. That's all you need to carry on your analysis. Okay, all these three questions, they have something to do with calculating the normal probability, and we do have a shortcut or kind of like a cheat sheet in R. So this is what you want to do. If you have something that is normally distributed, if you want to find smaller than, you can just use the keyword p-norm. And if you want to find the probability of greater than, then you have to first find smaller than and then use 1, subtract that quantity, whatever quantity that is. And if you want to find the in-between probability, there is some more work to do. So let's see how to apply these rules in a real question. So first thing you want to calculate is the probability of smaller than. So as we talked about before, we just type this command because that thing is designed for calculating smaller than probability. So 15,000, and mean is from the information 1400, and the standard deviation is 100. So you run this line of code, and this is the probability, 0.84. Next up, if you want to calculate the probability between 1,325 and 1,500, this is what you want to do. See this line of code, we want to do something like this. We can just go ahead and copy this directly. So we have to replace A as the bigger one, which is 1,500, and B is the smaller one, which is 1,325, and mean is still the same. Sigma doesn't change either. So if we run this line of code, which is 0.6147, and that gives the probability of randomly selected variable that falls in between 1,325 and 1,500. Okay, the last thing, if you want to calculate the probability that any randomly selected y is greater than a certain threshold, you have to use that function p-norm, find out the flip side, and then use 1 to subtract it. So for instance, part C, it is given by 1 minus p-norm 1325, and still the same mean and the same standard deviation. So this 0.77 is a probability that actually a randomly selected y is greater than 1325. Of course, as we discussed before, equal sign doesn't matter in a continuous case because we have defined any point probability in a continuous variable as 0, so you don't have to worry about that part. This one is a little different because the previous three questions asks for probability, but this one asks for quantile. If you are still fuzzy about the difference between them, and this is what it is. If you know what happens on the left hand side and you just want to calculate the right hand side, then it is a probability. In other words, the Q here, that quantity is a probability. However, if you know what Q is, but you want to find A, in this case A is unknown, then you are finding quantile. So let's see how to use this knowledge in this question. We are given that in this normal distribution we have mean 88 and standard deviation is 7. We want to find the 65th percentile. You use Q norm, which is for quantile of normal distribution, and it gives you 90.697. What does this mean? 65% of all the data that you have collected averagely is smaller than the threshold 90. So that is what the percentile means. And the next question is find the 35th percentile. And similarly, you just replace this 65 with 0.35 and you get 85.30276. So that is the 35th percentile of this normal distribution. This is an interesting one, and I want you to recall the different tools that we talked about in order to figure out if our distribution is normally distributed or not. Some common tools that people use includes box plot, QQ plot, empirical rule, and histogram. I guess there are multiple ways to approach this problem, but I would recommend you to use empirical rule, because empirical rule tells us like 6 to 8% of all the data will be around one standard deviation of the mean. But if you actually do the math in this case, that 6 to 8% interval will be 0.09 negative, 0.13 positive. And if this distribution is normal, if this distribution is symmetric, this means almost 30%, which is like half of 6 to 8%, is negative. And we are talking about rainfall here, which cannot be negative. So here we arrived at a contradiction, and that is why I think this cannot be from a normal distribution. It has to be something else, which is probably highly skewed. Okay, this question boils down to find the in-between probability. If you read the question itself, it actually asks you to find the probability of y bar in between maybe 48 and 52. And in the second case, part B, it asks you to find out the probability of y bar in between maybe 98 and 102. So the only hard part is to find out the distribution of y bar itself. So this goes back to the conclusion that we talked about so many times in class, which is the distribution of y bar. It is the sampling distribution. So if the population distribution is mu and sigma, then the sampling distribution is mu and sigma over square root n. That is the sampling distribution of y bar, and we want to use that piece of knowledge to solve this question. So as you can see here, I defined the new standard deviation, which is for the standard deviation of y bar. I used the original sigma divided by square root of sample size, which is 64. And in the first case, we are already given the mu, which is 50. So what we want to find out is actually the probability of y bar that is in between 50 minus 2, which is 48, and 52. So we want to find a quantity like this. So as you can see in the cheat sheet here, we can actually use this line of code here. We have to change our A into 52 and B into 48 because we want the probability between 52 and 48. And mean is 50. So we change it here, or if you run this line, R already know that the mean is 50, so you can just keep it here. And the sigma is the new SD because the sampling distribution will have a different standard deviation compared to the population distribution. So if we run every line of this script, so this is the probability. Actually what this says is the probability that y bar lives between 52 and 48 is 0.89. And similarly, you can work on the second part of this problem, in which you just change mu to 100. So it's kind of simple. We can do it here. So on this side, it has to be 100 plus 2 instead of 50 plus 2. The mu here, we have to change it to 100. And here is 100 minus 2, and the mean is still 100, and the new SD is the same because the standard deviation applies to both of these cases. So if we run this line of code, it will give you 0.89.04, which is exactly the same with part A, because if you look closely into these two cases and compare them, we did not change standard deviation. We just shifted this location from point A to point B. That does not change anything.